Okay, so in this video we are going to be talking about reaction rates, and we're going to talk about the things that are going to impact how quickly or slowly a reaction takes place. Okay, before we even start to talk about reaction rates and how fast reactions go and the things that are going to impact those reactions, I wanted to talk about molecular collisions. And there you need two things in order to have a successful, well, you need to have molecular collisions to have a successful reaction. And there are two components to successful molecular collisions. The first is that those molecules must collide with the correct orientation. And so in this picture here, what we have is we've got carbon monoxide reacting with oxygen. If the carbon monoxide if the oxygen end of the carbon monoxide interacts with the oxygen, nothing will happen. They'll just literally hit each other and bounce apart. If they are oriented so that the carbon end of the molecule, carbon end of the carbon monoxide, interacts with the oxygen, then you will have a reaction. Okay, so they have to line up and be oriented correctly. The other piece of this is that the molecules must be moving fast enough to break the bonds of the reactants, right? If they just kind of slowly bump into each other, chances are they're not going to collide with enough force to break the bonds. But if they are moving super fast and they hit each other, there's probably going to be enough energy to break those bonds and get that reaction to move forward. Okay. So the reaction rate is defined as how quickly a reaction will proceed, or how fast a reaction will proceed. And we'll talk about several factors that are going to affect how quickly that reaction will take place. The first is temperature. And the rate of the reaction will increase with increasing temperature. And that is because temperature is directly related to molecular movement. The higher the temperature, the faster those molecules are moving. And if those molecules are moving faster, the chances are they're going to collide with enough energy to break the bonds, resulting in successful collisions. You're also increasing the number of times those molecules collide with each other if they're moving fast, which means you're more likely to have the correct orientation when they collide. Okay, so we've talked about the fact that you need to have your molecules moving fast enough, right, in order for that reaction to take place. So as you increase the temperature, you're going to increase the rate of reaction. We've talked about the orientation, right? Those molecules have to be properly oriented in order for that reaction to take place. Second thing that's going to impact how fast that reaction can take place is the presence of a catalyst. Now, a catalyst is going to increase the rate of the reaction without actually being used up in the reaction itself. As we're going to see in a moment, that catalyst is going to lower the activation energy. That is the energy that's needed for that reaction to occur. That's the initial amount of energy that has to go in to help get those bonds broken. So a catalyst is actually going to lower that activation energy and allow that reaction to proceed quicker. Okay, so this is a diagram. So there are two different types of catalysts that we're going to talk about. The first one is an enzyme. And for those of you going on to 1211, you will spend a bit of time talking about enzymes and how they work, and how they help to lower the activation energy of reactions and allow reactions in the body to go quicker. So an enzyme is a catalyst, right? It's a biological catalyst, and what it does is it has a very specific shape that allows it to directly interact with a reactant. So in this case, you have this enzyme that is reacting with a very specific substrate, and that enzyme is designed to take that substrate, has a very specific shape to it that allows it to grab that substrate and allows for that reaction to happen much quicker. So lactase would be an example of an enzyme that allows for the digestion of lactose, the milk sugar. For those people who are lactose intolerant, that means that they don't have that lactase enzyme, which does not allow them to properly digest lactose, which makes consuming dairy products rather problematic and a little uncomfortable. What you see over here on the right-hand side is what's called an energy diagram, and we're going to spend quite a bit of time talking about these. But what you see right here is this hump, this initial hump. So you have your energy, the amount of energy that is either going into that reaction or being released from that reaction. And then the reaction coordinate is essentially the amount of time. And so what you can see here is this piece right here and this piece right here. This is your activation energy, and I'm just going to label that with an AE. Okay, so that is your activation energy. With the enzyme, that activation energy is significantly lowered. Without the enzyme, it's significantly higher. So the higher the activation energy, the slower that reaction is going to take place. And so that catalyst is going to help make that reaction move forward by lowering that activation energy. So another catalyst that you may or may not be aware of are the catalytic converters in our cars. And I'm old enough to remember having to have a catalytic converter, my parents having to have a catalytic converter put into their car. They had an old 1968 Mustang that was produced before catalytic converters were regularly put into cars. And so this was a bit of a problem because in addition to carbon dioxide being in your exhaust, you may have also had carbon monoxide, which is a pretty common toxic gas in exhaust. You may have also had nitrogen monoxide, which is a component of acid rain, also being released into the environment. And so these catalytic converters were installed into cars to essentially catalyze 3 reactions, which you can see here, to reduce the amount of toxic gases that were being released into the environment. Especially the nitrogen oxygen components, those contributed to acid rain, and so that was a large problem in the 1970s into the early 80s. On the right hand side, and I'm just going to want to tell you to just ignore that for right now, again showing the difference between having no catalyst and having a catalyst in your car to help with those reactions and help break those reactions or those toxic gases down. It makes that reaction go significantly quicker. And the last component for something that will impact how fast a reaction proceeds would be the concentration. So think about the amount of reactants that you have, the number of particles. And I personally need visuals, and so I generally, when I think about something like this, I think about trying to walk down a hallway, right? And how many people am I going to physically bump into if the concentration of people in that hallway is very high, right? I'm likely to bump into people if there are a lot of people crowding the hallway, whereas if there are only a few people in the hallway, I'm less likely to bump into somebody. Same thing here. The rate of your reaction will increase when the concentration of each of your reactants increases, and that's literally just because of the sheer number of particles available for collision. The more collisions you have, the more likely it is that you are going to have an effective collision.